Welcome to Q News Deep Dive. Today we're really digging into the Quantum Technology Monitor 2025. If you're trying to, get a quick handle on where the quantum industry actually stands right now.
Not the hype, but the real market move.
Exactly. The momentum, the strategy. This is your shortcut.
And that's our mission here, really, to pull out the key strategic insights, the investment trends, and make sure that even if you're just starting to learn about this field,
Which many people are.
right, you walk away understanding these complex ideas and seeing the real acceleration happening in the quantum market.
Okay, so let's start with the basics. The quantum universe, people talk about quantum technology, QT, like it's one big thing.
But it's not, really. It's more like three distinct fields.
Yeah, three pillars. The most famous one is probably quantum computing, or QC. This is, using quantum physics for a whole new way of computing.
Aiming to tackle problems classical computers just choke on, like really complex simulations or optimization tasks.
Then pillar number two is quantum communication, QComm.
This one's all about security, sending information in a way that's fundamentally secure, protected against even, unlimited computing power.
Provably secure, that's the key phrase there. And the third one, often overlooked.
Quantum sensing, QS, which is fascinating. These are next-gen sensors.
Super, super precise measurement devices, right? For things like gravity, time, magnetic fields.
Yeah, providing accuracy that's just orders of magnitude better than what we have today.
Okay, so QC gets most of the attention. Why is it potentially so powerful? What's the core physics behind it?
Well, it leverages a couple of really counterintuitive quantum effects.
Yeah.
For anyone new, let's try a simple analogy for the first one. Superposition.
Okay.
Think of a regular light switch. It's either on or off, 0 or 1. A quantum bit, or qubit, because of superposition, is more like a dimmer switch.
So it can be on, off, or somewhere in between.
Exactly, and crucially, it can represent all those possibilities simultaneously. This lets a quantum computer explore a vast number of potential solutions all at once.
Instead of checking them one by one.
Precisely. And the second big one is entanglement. Einstein famously called it spooky action at a distance.
Right. This is where two qubits become linked.
Intrinsically linked. Doesn't matter how far apart they are. If you measure the state of one, you instantly know the state of the other. They behave as one single system.
So QC uses both this simultaneous possibility thing, superposition, and this linked destiny thing, entanglement.
To achieve massive parallel processing power for certain types of problems.
And the payoff for wrangling all this quantum weirdness, the monitor estimates QC alone could unlock something like $0.9 trillion to $2.0 in value by 2035.
That's huge potential value.
It really is. And big industries, too. Energy, pharma, finance, logistics. $2 trillion, just to put that in perspective. That's bigger than the GDP of Canada or South Korea.
So we're talking about a fundamental economic shift if this pans out.
Definitely. Okay, let's zoom right into the money then. Because the report makes it clear we're past the pure lab research stage now.
Yeah, there's a definite shift towards actual revenue.
Right. QC companies apparently brought in somewhere between $650 million and $750 million in 2024.
Which is already significant.
And the forecast is they'll break $1 billion by the end of 2025. That curve is steepening. It signals real commercial traction, doesn't it?
It absolutely does. And the investment numbers back that up strongly. Funding for QT startups, it jumped by about 50% year over year.
50%? To what total?
Reached $2 billion in 2024. Now, what's interesting within that number is the split between private and public money.
Okay.
Private funding is still the lion's share. Around 2/3, 66% of that $2 billion total came from VCs and private investors.
But you said there's an interesting split. So the public side.
That's where the big change happened.
Yeah.
Public funding saw a really significant jump. It increased its share by 19 percentage points compared to 2023.
Wow, 19 points. So governments are really stepping up. What changed? What are they suddenly seeing?
I think it's a growing recognition of the sheer strategic importance, geopolitically, economically. Controlling this tech is seen as crucial.
And that recognition seems to have exploded right at the start of 2025.
It really did. Look at the numbers. Public funding announcements were $1.8 billion for all of 2024.
Okay, $1.8 billion for the year.
But just in the first few months of 2025, those announcements already shot past $10 billion.
$10 billion in just a few months.
Yeah.
That's not just stepping up, that's a massive surge.
It's a staggering acceleration. And most of that, $7.4 billion, came from one country, Japan.
Japan, really?
Yeah.
Why such a huge front-loaded commitment specifically from Tokyo? That feels like more than just basic research funding.
Oh, it absolutely is. It signals quantum tech is now a top national priority for them, a strategic repositioning.
How so?
They're explicitly linking this quantum funding with their pushes in next-gen semiconductor research and high-performance computing. They're basically saying, we need to own a piece of the foundational tech for the quantum era.
So it's an economic and national security play, a bid for leadership.
Exactly, an urgent one. They don't want to be left behind.
And looking further out, this kind of commitment aligns with the report's long-term market view, right?
It does. The estimate for the total internal market, so that's the infrastructure, hardware, software, services, could hit around $198 billion by 2040.
$198 billion. And QC is expected to be the biggest piece of that pie.
Yes, projections for QC range from $45 billion up to maybe $131 billion of that total by 2040.
Okay, that's a huge potential market. But all this money, all this excitement, it's all riding on solving a massive technical problem, isn't it? Reliability.
That's the absolute core challenge. Qubits are incredibly fragile. They lose their quantum state. They decohere really easily due to noise, vibrations, anything.
So all this progress depends on making them stable, which means the top priority strategically has to be what? Quantum control.
Quantum control and critically error correction. This is the make or break hurdle right now.
So the big news in 2024 wasn't just building more qubits.
No. It was about figuring out how to use the ones we have reliably. Error correction isn't optional anymore. It's essential.
And the breakthrough idea is about combining qubits.
Exactly. Taking lots of these noisy, unstable physical qubits.
The ones we can actually build.
Right. And using them collectively to encode a single, stable, much more reliable logical qubit. That's the path to fault tolerance, to computations that are actually accurate.
And we saw real progress on this front in 2024 from major players. Google, for example.
Yeah, Google published results using their 105 qubit Willow processor. They showed they could suppress errors. But the really crucial finding was how.
What did they find?
As they used more physical qubits to encode their logical information, the error rate didn't just go down, it went down exponentially.
Exponentially. So the bigger the system got, the more reliable it became, relatively speaking.
Exactly, which is kind of counterintuitive, but it's precisely what you need to see for this approach to work at scale. It proves the theory holds promise in practice.
Okay, that's significant. What about other approaches? It's not all superconducting qubits like Google's.
All right, look at Quera. They work with a different platform, neutral atoms. These are known for being quite stable and well-connected.
And what did they achieve?
They demonstrated a programmable processor with up to 280 physical qubits. It shows scalability isn't limited to just one hardware type.
So progress across different platforms. And AWS also had a key announcement, didn't they? Using something called cat qubits.
Yes, and this was potentially very important for efficiency. They showed a method to encode one logical qubit using only 9 physical qubits.
Only 9. Now, for listeners maybe not deep in the weeds, why is that 9-to-1 ratio such a big deal?
Because historical estimates for fault tolerance often talked about needing thousands, maybe even tens of thousands, of physical qubits for just one stable logical qubit due to all the noise.
Thousands to one. Okay, yeah, 9-to-1 sounds much better.
It's a massive potential improvement. If that kind of ratio holds up and proves stable enough, it dramatically shrinks the sheer amount of physical hardware you'd need. It makes building a useful fault-tolerant machine seem, well, much closer and potentially less incredibly expensive.
That could really shorten the timeline. Okay, let's shift gears slightly to the, let's call it the knowledge landscape. Patents, publications. How's that race looking?
Well, overall QT patents, granted globally, went up about 13% in 2024. And the U.S. still leads in the total number of granted patents across all the quantum fields combined.
Okay, U.S. leads in granted patents, but you said but.
But there's a really important distinction. If you focus specifically on quantum computing patents,
Just QC.
yeah, China is actually leading globally in the number of QC patent applications filed. They account for about 32%.
Applications, not granted patents.
Right. And China also leads significantly in scientific publications related to QC, around 42% of the global total in physical sciences papers.
Okay, help me understand the significance. If the U.S. has more patents already granted, doesn't that mean they currently own more existing IP? Why focus on the application pipeline from China?
Because granted patents often reflect research done, several years ago. Applications and publications, on the other hand, show where the current research activity and, crucially, the strategic focus is right now.
Ah, so it's a leading indicator of future capability.
Exactly. It suggests China is pouring resources into the QC commercialization pipeline today. They seem intensely focused on translating research into actual products and systems very quickly. It signals a major push for future market share, even if the U.S. has a lead in some of the foundational IP from the past.
That geopolitical angle definitely fuels the competition. We saw more startups too, right? 19 new ones in 2024.
Yeah, up from 13 the year before. And interestingly, most of those new companies, 11 out of the 19, popped up in either equipment and components or in application software.
Okay, components and software. Does that tell us something about where the value is expected to flow in this market?
Absolutely. Right now, today, the companies making the specialized equipment, the dilution refrigerators, the lasers, the control electronics, and the core components, they capture a lot of the value.
Makes sense. You need the building blocks first.
But look ahead 5 or 10 years, maybe longer, towards full uptake. The expectation is a major shift. As the hardware matures, becomes more standardized, maybe even commoditized.
Like classical computer hardware did.
Precisely. The high-value slice of the pie is expected to move significantly towards application software and services. The companies developing the quantum algorithms for specific industries, the platforms to access QC, the consulting, that's where the big margins are projected to be.
That's a key insight for anyone watching the space. The long-term value might be less in the box itself and more in what you can do with the box.
Couldn't have said it better. And geographically, this growth isn't happening everywhere equally. It's consolidating.
Into clusters, right? Like Silicon Valley for classical tech.
Exactly.
Yeah.
We see established quantum hubs like Boston and Chicago continuing to grow stronger. But what's really noticeable is how quickly new hubs are emerging.
Where?
The report specifically calls out Seoul, Tel Aviv, and Abu Dhabi as rapidly developing clusters, often boosted by strong government backing and international partnerships.
So the race is global, playing out in these specific hotspots. And even within the U.S., it's not just national, it's state-level competition too.
Very much so.
Yeah.
Illinois, for example, committed $500 million for quantum infrastructure to bolster the Chicago cluster. And Maryland launched a big initiative aiming to pull together over $1 billion in public and private money for its quantum ecosystem.
Wow. So states are competing to become the quantum hook. It shows how seriously this is being taken at all levels.
This intense drive, all this progress,
Yeah.
it inevitably brings us to a really critical and frankly urgent topic, security. And the conversation here is dominated by one concept, Q-Day.
Okay, let's define Q-Day very clearly for everyone listening. What is it?
Q-Day is essentially the projected point in time when quantum computers become powerful enough to break the encryption standards we rely on today.
Specifically things like RSA 2048, the algorithms protecting most secure websites, financial transactions, government communications.
Exactly those. Once a quantum computer can factor large numbers efficiently using Shor's algorithm, that type of public key cryptography becomes completely insecure.
And the urgency isn't about waiting until Q-Day arrives, is it?
Absolutely not. The urgency is now. Think about sensitive data that needs to remain confidential for decades. Health records, intellectual property, government secrets, long-term financial contracts.
Right. If that data is encrypted today using algorithms vulnerable to future quantum computers,
Then it's already at risk. Someone could be harvesting that encrypted data now, just waiting for Q-Day to arrive so they could decrypt it later. It's sometimes called the harvest now, decrypt later threat.
Okay, that's sobering. So what's the solution? This is where quantum communication, QComm, comes back in.
Precisely. And it's why that market is already booming. It was about $1 billion in 2023, but it's projected to soar to between $11 billion and $15 billion by 2035. That's a compound annual growth rate of 22–25%.
Huge growth. What are the main technologies within QComm fighting this threat? The monitor mentions two key approaches.
Yes, there are two main lines of defense being developed and deployed. The first, and the one that's more commercially mature right now, is post-quantum cryptography, or PQC.
Post-quantum, so after quantum computers? But what is it exactly? Is it using quantum tech?
No, and that's the crucial part. PQC uses classical algorithms. They're just designed differently based on mathematical problems believed to be hard even for quantum computers to solve. Think of it like a software upgrade for our current systems to make them quantum resistant.
Okay, so PQC is a classical software fix. What's the second approach?
The second approach is truly quantum key distribution, or QKD.
QKD, how does that work?
This uses quantum mechanics itself, principles like superposition or entanglement, to securely distribute cryptographic keys between two parties. The laws of physics guarantee that if anyone tries to eavesdrop on the key exchange, the quantum state is disturbed and the attempt is detected.
So it offers provable security based on physics, not just mathematical assumptions like PQC.
Exactly. QKD is a hardware-based solution,
Yep.
generally more complex and expensive to implement currently, but it offers, in theory, the highest level of long-term security assurance.
Okay, so we have PQC as the more immediate software-based transition and QKD as the longer-term hardware-based gold standard. Who's adopting these right now?
As you might expect, governments are the biggest customers today, driven by national security concerns. They held about 62% to 66% of the QComm market share in 2023.
Makes sense, but that's expected to change.
Dramatically. The private sector is waking up to the risk, especially sectors with highly sensitive, long-lived data. Telecommunications is projected to grow its share from maybe 2–6% in 2023 to potentially 16–26% by 2035.
And finance.
Financial services, too. They're expected to reach somewhere between 14% and 24% market share by 2035. They understand the Q-day threat to transactions and long-term records.
Okay, for our last segment, let's pull back a bit. We've talked about QC, QComm, QS, but quantums isn't just its own little world, is it? The report frames it as a key enabler for other technologies.
Absolutely. It's poised to have powerful synergistic effects across the tech landscape, especially with AI and machine learning.
Ah, the AI connection. How does that work? Is it a one-way street, QC helping AI?
No, it's definitely a two-way symbiotic relationship. QC can absolutely help AI.
Oh.
Quantum algorithms show promise for speeding up certain parts of AI training, particularly tasks involving complex linear algebra, and potentially QC could help overcome some limitations classical hardware faces with massive AI models like the memory wall or sheer compute power constraints.
Okay, so QC boosts AI. How does AI help QC? That seems important given the reliability challenges we discussed.
It's incredibly important. AI and machine learning models are proving very useful in developing quantum tech itself. They can help optimize quantum algorithms, design better quantum circuits.
And the error correction?
Critically, yes.
Mm-hmm.
AI can automate the complex calibration and tuning needed for qubits and develop smarter error correction strategies. Essentially, using AI to help tame the quantum weirdness and build those stable logical qubits faster and more effectively than humans could alone.
That's a fascinating feedback loop. AI helping build better quantum computers, which in turn will run more powerful AI. Okay, besides AI, what other big synergy areas does the monitor highlight? Where might we see early impact?
I think sustainability in climate tech is a really promising one.
How so?
QC is incredibly well suited for molecular simulation. This could revolutionize the discovery of new materials, things like better catalysts for carbon capture, more efficient materials for solar cells, or components for next-gen battery.
And optimization, too.
Yes, complex optimization problems are another sweet spot. Think optimizing power grids to handle renewable energy fluctuations, or making global supply chains vastly more efficient, reducing waste and emissions. Even small improvements there, scaled up, have huge impacts.
Makes sense. The report also mentions robotics. How does quantum touch robotics?
It affects all three pillars we talked about. QC could provide robots with more powerful onboard processing for autonomous decisions. QComm could secure communication links, especially for swarms of drones or robots.
And quantum sensing?
QS could be huge for navigation. Imagine robots or drones that can navigate with extreme precision without relying on GPS, which can be jammed or unavailable indoors or underwater. Quantum sensors for acceleration and rotation could enable that.
Okay, and finally, broader cybersecurity. Beyond just preparing for Q-Day.
Yeah, even before fault-tolerant QC arrives, quantum principles can help today. Quantum algorithms might improve threat detection by finding subtle patterns in huge network traffic data sets. And quantum random number generators, QRNGs, are already a commercial product.
QRNGs. Why are random numbers important?
True randomness is fundamental to strong encryption. Classical computers are surprisingly bad at generating truly unpredictable random numbers. They use pseudo-random algorithms. QRNGs leverage quantum mechanics to produce genuinely unpredictable randomness, making cryptographic keys much stronger.
Got it. Okay, so pulling this all together, what's the main narrative emerging from the 2025 monitor?
I'd say the main story is that the quantum ecosystem has clearly hit escape velocity. We're moving past the era of purely theoretical research into a phase of tangible engineering, early applications, and real revenue generation.
Driven by?
Driven by, one, these massive global investments we're seeing from governments like Japan and focus clusters, and two, crucially, by genuine technological progress, especially these breakthroughs in error correction that are finally making quantum systems stable enough to start thinking about practical use cases.
Right. The lab experiments are starting to look like proto-products. We know innovation speed isn't just about money. It's hitting technical milestones, adhering to roadmaps, seeing partnerships form. We've seen steps like Google's exponential error suppression. It really makes you think.
What's next?
Yeah. Given this pace, what unanticipated breakthrough might be the real trigger, the thing that suddenly accelerates everything? Will it be a completely unexpected leap in qubit stability, maybe from a new material or technique? Or could it be a novel quantum algorithm that turns out to be way more efficient than we thought, dramatically lowering the bar for Q-Day? That's the question to ponder.
Which unknown will be the tipping point?
Exactly. Thank you for watching today. This was Q News Deep Dive.